Michela Mapelli, and she will talk about something else in a little while. We'll start with a visitor from the University of York, Tom McLeish. Where is Tom? Here. Who is doing fascinating work, and in fact had two options for a presentation, but we selected the one that relates to interdisciplinary investigation of a medieval mathematical cosmology from the 30th century, where people might have contemplated the Big Bang Theory. We're all looking forward to hear about that. And then we'll hear from Parriott, who will tell us about why you should care about OCO, NDD, BCA, and other federal budget Arcana. And then we'll hear from Michela Mapelli from Padova about supernova-driven extreme mass ratio inspirals. And finally, from another visitor that is here from CITA, Hamsa Padmanabhan. Where is Hamsa? Over there. You might recognize her last name. She's the daughter of Tanu Padmanabhan. I started astrophysics as a result of reading many of his books, and it's a great pleasure to host his daughter, who is working on cosmology and has a very interesting line of research of her own that you will hear about. And she will talk about going beyond lambda CDM with H1 intensity mapping. Before we start, I just wanted to mention that in today's newspapers there was a story that could be of great interest since the ITC is about computation. It's a milestone that was announced by Google yesterday, a Nature paper that was retracted, but it's not completely public. But the idea is quantum supremacy. That's a term that was coined back in 2012. And the idea is that the quantum computer, at least the one that Google constructed, is capable of solving a problem, not necessarily a useful problem. Just like the Wright brothers flew a plane that was not used for commercial purposes at first. So it can solve a problem within 200 seconds that it would take a conventional computer 10,000 years. Okay, so that shows that 10,000 years by practical standards is a very long time, but for us it's not very long. But for the people in the field, they feel that it demonstrates that quantum computers are really the wave of the future, and that the main difference from regular computers, instead of having bits of 0 and 1, you have a combination that is called the qubit, and with the qubit you have a mix of two states. With 2 qubits you have 4 states that are mixed, and it grows exponentially with the number of qubits. So we have 53 as claimed. It's a huge advance in our ability for computations. And these, if you look at the picture of these quantum computers, they look very different from the regular computers that we're used to. So this is a milestone that marks a new era, and perhaps we'll hear about it at the ITC in the future. Anyway, Tom.
Okay. So in that sense, this is a quantum seminar. In other words, this is a 10-minute talk, I understand, that would normally take about 10 hours. But I'm delighted to be here. I should say, I went to Tom McLeish from University of York. I'm a physicist. Some people say you must be a historian of science. I'm not. I'm a physicist. This is a really interdisciplinary project with historians and medievalists. Please suspend everything you were once told, like I was at school, that there was no science before Newton and all that. It's all nonsense. And there's some fascinating stuff going on in astronomy. I should also say I'm a soft matter theoretical physicist. I'm also an interloper for those reasons as well. But astronomy was always my first love. It got me into science, and I have one paper in the Astrophysical Journal, but that's for another time. Okay, so here we go. This was the days when, we think we write manuscripts, but we don't write manuscripts. That's a manuscript. Okay, that's a manuscript. They used to really write manuscripts in Latin, on vellum or parchment, and they last for 1,000 years. You can't tear this stuff. This is from the Durham's Library in the Bodleian. The author we're going to meet is this guy. One picture of him. He was master of the liberal arts. Otherwise, he taught them mathematics to the Oxford Franciscans in the 1220s. Robert Grosseteste, name means big head, and he became Bishop of Lincoln later on, which is why he's got the funny hat. He's extraordinary. He wrote in the 1220s. He wrote treatises on light, colour, sound, motion, the spheres, and I just got fascinated about 10 years ago. What does a 21st century physicist think when she or he reads a treatise on light written in 1224? And that's what you read. Now, this is Harvard, so I didn't think you needed the Latin translated. So while you're working your way through that fabulous piece of insight, I'll explain why I found this piece so extraordinary myself. I don't know what I expected. He was talking about, light as the Trinity or some holy religious thing, but he's not. He doesn't talk about light to start with. He talks about the problem of the stability of matter. He says, I'm worried about classical atomism is not a good theory for the stability of matter because classical atoms are indivisible particles. They have no volume. They have no, and he says, however large a number of a zero volume thing I still have zero volume. So he's put his finger on the fact that classical thinking, including the classical atomism which he was reading in Aristotle and Plato and so on, doesn't explain the solidity of matter or why we can't fall through those chairs. So that's what, in other words, two galaxies. It's he understands that we in the chair ought to interact like two galaxies, where effectively stars are point, like you know about this, and I'm just indulging you. Okay, and then this is extraordinary. He says whatever it is, but then he says I do know something that has the properties of space filling, and that's light. I observe it. So he develops this physics of this amalgam physics that matter is point like atoms, given stability by light, or if it's not light, it's something that has the same properties as light. Oh my goodness! So he does other wonderful things. He's impressive that he knows that you've got to write about the cosmos in the language of mathematics. So he describes, for example, divisions of infinite series. He says it's a bit like this infinitely propagating light gives us finite volumes because the infinitesimal volume of the atoms is inflated to a finite ratio by the infinite multiplication of light. So he talks about he doesn't have a good concept of limits, of course. He's just groping in the dark about this. But nonetheless, the fact that he's describing the world in mathematics is interesting. What is even more interesting is he then takes this in this treatise 1224. He takes this notion, this theory of matter, and he wants to apply it to some examples. And he basically says, let me think of the largest example I can think of. That's the whole universe. Right, so what does his light inflated theory of matter say about cosmology? It says this: light at the beginning of time extended matter, drawing it out along with itself into a mass the size of the world machine. Machina mundi is the Latin for universe. In other words, he has light beginning, the world beginning as a point of light, which then expands into a sphere. Oh my goodness, well, we had that before. It's an interesting thought. Now, of course, let's not be anachronistic about this. This is medieval thinking, however sensitive it is. And of course, the universe is not our universe, it's the geocentric universe. It's the universe that you assume you've got before you have telescopes and can measure parallax and stuff like that. There's no observed consequence of the motion of the Earth, so it's, and everything seems to go around in spheres, so it's the spheres. So, and I'm teasing out some fundamental physics here, because he then goes through a series of axioms that this medieval Big Bang has. So the idea is that light extends matter down. But of course, since the ancients, there was strong idea that you could have no vacuum. But if you can't have a vacuum, then you must have a minimum density, right? So you've got this expanding matter. Where does the minimum density first occur? Answer: on the edge, which is where the universe must freeze off or purify. There you have your firmament, you see. Perfect matter also radiates. So you now have an inward radiating flux called lumen, which pushes matter inwards now rather than outwards. And every time you reach this purification criterion, you get a crystalline sphere. So here are the 6 physical laws of the Grosseteste cosmology. Light, first corporal form, gives tension to matter, expands into sphere instantaneously. Light multiplies infinitely, matter is conserved, there exists a minimum density, and perfect material emits light, and in it comes. He does something else which is extraordinary. Now, you just make sure you understand. The medieval cosmology inherits its cosmology from Aristotle and Plato, of these nested spheres. The idea was the universe is, we would say, symmetry broken. In other words, above the orbit of the moon, everything was perfected in this sense, and all motion was circular. Yeah. It's kind of obvious when you see. And below the orbit of the moon, where the elements of fire, air, water is, everything is imperfected, and motion is not circular. It's mostly up and down and rain, and everything gets mixed, and it's all suffering and woe and ghastly, right? So you have to explain this symmetry breaking. But he does it. It's very clever. Because the inward propagating light front is perfecting matter as it goes, but the matter's becoming denser and denser and more recalcitrant, right? Meanwhile, the light is getting absorbed and getting weaker and weaker, and eventually there's a crossover, and there's not sufficient power in the incoming radiation to reach these purification transitions, and that's the orbit of the moon. So you get a symmetry breaking. And from a uniform set of axioms, you get a symmetry broken universe. So, yeah, I find it's, because it's wrong. Of course, I'm not selling you the Aristotelian universe, but it's wrong in a really interesting way, which is frankly what we try to do most of the time, my thesis. I just hope it's wrong in interesting ways. So now the other bit of this project we invented, we're having great fun here. And by the way, the reason that this project works so well is if you're good enough at Latin and medieval philosophy and history to read the text in the first place, you gave up the maths and physics you need to understand what you're reading when you're about 13 years old. At least you do in Britain, right? So you have to work together, and we can't read. So we did this. So a little bit of fun now. Let's have some real fun. If you're prepared to translate the Latin, here's the Latin, you've all got that near because you're Harvard scholars, into English, if what the text is talking about is quite well definable mathematical interactions of light, motion, so on, there's no reason why you shouldn't just translate into another language, right? Okay, why not? Why not? And even the humanities scholars, they thought this was weird, but actually, of course, every time you translate something, it's not just a code for code. Translation is much richer than decoding, right? Translation forces you back to look at the text in new ways, and we've been able to do that. Ask me questions about that. Richard Bauer joined the team. Maybe some of you know Richard. He's one of the team in Durham, the Centre for Computational Cosmology. And Richard did the obvious thing and coded up the Gross test equations to see what would happen. So we have a little Python code now which can generate to you medieval universes. Boom. And here it is, competing away. We've had the instantaneous extension. Here's the incoming flux of lumen, and every time it reaches a finite ratio, a whole number ratio of the crystallization condition, you get a new sphere. And so it turns out that this guy was right. Well, if you translate, do the obvious thing, translate his Latin into English and into mathematics, you can write a little code which computes medieval universes, and there's one going. We actually had to go back into the text to see where he talked about absorption, because we didn't get absorption at first in there. If you don't have absorption, then you just get an infinite number of shells. You don't get the phase transition. Nearly there, Abby. I'm seeing getting shifty. It turns out that the model, as I said, there are a few parameters. Of course, there are a few parameters we don't know, and it's in fact the parameter space is three-dimensional. There's a three-dimensional parameter space. It's things like the light-matter coupling and the absorption coefficient. And as you wander around this parameter space, you can get medieval universes with different numbers of planets. Okay, and there's 10 planets, and this is 10 spheres. The sun and moon are on planets as well. And these are not until you get areas with no planets at all. So you have a sort of medieval multiverse. It's interesting that in Gross's original text, he knows that his physics doesn't tell you the number of spheres. So he actually calls on this Pythagorean mystical third triangular number of 10, and that's his way of doing this, to say now why there are 10. So what a little bit of reception here. You probably know about this guy. Is that the end of it? Okay, so the question, might Georges Lemaitre, the Catholic priest and theologian who solves Einstein's equations, might he have known about Deluce of Gross test? And the answer is he might well have done, because when he was working with Eddington, a group of people went from Cambridge to hear a lecture on Gross test, Big Bang, cosmology. And thank you for listening. AudioUniverse.com, there we are. And after 10 years of hard labour, first OUP volume of a 6-volume re-edition of Gross test scientific works coming out this November. Boom. Thank you. Right. Yeah, exactly. Well, it's very interesting because Richard said.
The only thing that they were missing is, of course,
Absolutely.
promoted science in the world.
Absolutely.
And the other thing to think about is what would future generations think about those people nowadays that do not use data at all and just come up with speculations about string theory, the multiverse, and so on. Will it be as good as this guy?
Yeah, absolutely. Well, Richard Bauer said a beautiful thing. He said two things, because he confessed afterwards. He said, Tom, I've got a confession to make. When you invited me to be the cosmologist in this project, I thought it would take me 3 days to persuade you to point out this guy was stupid, silly, dogmatically constrained, not probably thinking. And then after I'd read a few pages into this, I realized I was reading a genius. And that's fantastic from a, absolutely fantastic from a leading galaxy cosmologist today. And that's the first thing he said. Then he said, and I really wonder what people in 800 years' time from now will think about all this dark matter nonsense we're talking about now. And I wish that, basically, Richard had exactly those two thoughts. Thank you. I think it was Aaron, yeah.
I was just curious, how did this work survive
Yeah.
for 800 years?
Yeah. Well, yes, I can. Yeah. Well, the answer is they wrote this stuff with very, very, very strongly coloured ink, which doesn't fade, on vellum, which is this special form of stretched animal skin, stretched sheep skin. This stuff is as indestructible. It's much, much harder to destroy than paper. And libraries all around the world. Harvard, Princeton in the US, Penn State, people have collections, or the Oxford and Cambridge libraries have had this. The Durham Library has an intact medieval library. It was never removed during the Reformation. So my home university, until I moved to York 2 years ago, has a whole big. The document I showed at the beginning is Durham University's manuscript A312, which is completely intact, and it'll be there in 3,000 years' time. And they look after it very, very, very carefully. But you can do, if you're a humanities scholar, you're used to this. I go to the Oxford Bodleian Library now, and I have massive imposter syndrome. They'll know I'm a scientist. They won't really bring out these things for me. But it's, and I understand why these people love it, because you can smell the vellum. The tactile, and you can see the little marginal notes that were made in 1142. And oh my God, it's really fantastic. Yes. Yes. But for everyone we know about, there are still thousands that are extant but not catalogued. So we still don't know what. And of course, I should say, the reason that 13th century is such an explosion of scientific thinking is because you just have Aristotle. Most of Aristotle's work were lost to the Latin West, preserved in the East and by the Arab Muslim scholars. And after the conquest of Spain, this is called the translation movement. All of Aristotle and the Arab commentators were brought into Western Europe, including some Jewish works by people like Maimonides, and that gave the efflorescence of science in the 13th century, which, as far as I can see, is the blue touch paper, that then slowly glowed brighter and brighter until, in a continuous way, until what we call the scientific revolution.
Well, this is in a way a continuation of two questions. First is, were there other people? I had not heard of Gross Test until today. And, were there other competing theories, extension theories? That's the first question. The second is about your book. Does the book contain not, really the translation all the way through to mathematics?
Yeah. Yes, it does. It does. Yes, it does. Yes. So this particular treatise isn't in the first book. The first book is his Introduction to the Liberal Arts and an extraordinary treatise on the generation of sounds. Which he describes in terms of normal modes of variation and coupling to air molecules, and how it's quite amazing. And we use the different scientific analysis of that. His contemporaries, yes, throughout this 13th century, there were quite extraordinary figures. So Albertus Magnus did for biology and plants what Grosseteste was doing for physics. Philip of Shareshill. In the century before, we have Adelard of Bath, who wrote an extraordinary text, as it were, to his nephew, including, for example, why gravity is. His nephew says, "Why don't people fall off the world if the world's a sphere at the bottom?" He explains why. Oh, by the way, just incidentally, if anyone here ever thinks that anyone ever thought that the Earth was flat, then just scrub that idea from your minds. That is completely made up. No one in the history of intellectual natural philosophy ever thought the Earth was flat. It was perfectly clear. It's right. Anyone with a brain from ancient times knows that it's round. And it's such a ridiculous thing. It's awful because these people were clever. The first time in history where there's actually ever been a serious group of people who think the Earth is flat is now. And it's true, and it's absolutely shameful. So anyway, so there were, and then of course, perhaps towards the end of that century, you have people like Roger Bacon. Roger Bacon is extraordinary. And then you have astronomy, but the great science of these centuries that goes on from the Baghdad and West right into the 15th, 16th centuries, optics, and it's a very, very fruitful and happy choice, because you can do things with optics. You can grind lenses. You can fill vessels with water. You can see the trace of the rays. And I think the triumph of optics is the solution of the problem of the rainbow. I read that Newton solved the rainbow. Newton really didn't write about the rainbow at all. The rainbow is much more subtle than prisms. It's not prismatic colours at all, actually, the rainbow. There's a whole other talk there. Grosseteste writes about the rainbow. But the first guy who writes about the rainbow is Theodoric of Freiburg, a Benedictine in southern Germany. And he does the experiments of glass spheres. He knows he's modelling raindrops. He gets people to make him glass spheres, fills them up with water, a little bit of dust, sunbeam, so you can see that the lights, these lovely drawings of the refraction of the back of the raindrop, refraction again. And then he sees some of the light bouncing twice. He says, that would give rise to another rainbow, bigger than the first one, a bit weaker, with the colours inverted. Oh, wait a minute. It gets a double rainbow. 1308. 1308. So we should know that there is some serious science done. So yes, there is of course, the number of people are very small, and they're in Freiburg and Oxford and Toledo and Hereford and a few Paris. Par excellence in Paris. But a bit of a community, and they're fascinating. Without them, we would not be where we are. We owe these people. These are the giants on whose shoulders I think Newton knew he was standing, actually. It's them. Fantastic. Really enjoyed it. Thank you. Thanks. Brilliant. Right. Oh, yeah, Mike. You want the mic?
Sure. Here, I'll plug you in while you hook yourself up. Keep getting alerts. Okay. So this is going to be less entertaining than the last talk. I know with a title like that's hard to believe. But Trump is somewhere in here, so that helps. Well, he'll be around a little longer. So thank you for the invitation. I will say to the folks, given where I am in particular, long ago in my life I did computational astrophysics, so I feel some of your pain. But now I only do Excel spreadsheets. So okay, so I have a bunch of slides, and I'm going to get through them in 10 minutes because I really only have one point, which will be at the very end. So it'll be easy to remember. So let's start with a famous Republican. So this is a quote attributed to Dick Cheney by Paul O'Neill when he wrote about his time in the Bush administration. Reagan proved deficits don't matter politically. There are no consequences for politicians of having huge deficits. So we'll spring forward from that to the Great Recession, have Obama coming into office, one of the first big things he does is get the Recovery Act passed in 2009. You can see a little wedge there for infrastructure and science. If $800 billion total, roughly 15 for science, 10 of that went to NIH, well, 9-ish and change went to NIH, and the rest to the science agencies. NSF got, I think, around 3 of that. If Paul Krugman was here, he would say 800 billion wasn't nearly enough, and that's why it took so long to get out of the Great Recession, but let's not go there. The bottom line is that for some reason, despite that advice from Dick Cheney, President Obama decided that deficits were a problem. So he started having discussions with John Boehner about what to do about the deficit, and they started putting proposals on the table. And here you have a Democratic president proposing cuts to Medicare, Medicaid, non-health, mandatory, agriculture, and a bunch of other things. You have, of course, tax increases, because it's a Democrat, and reform and ending tax cuts for the wealthy. The Republicans, on the other hand, not surprisingly, have larger cuts in spending and not as many increases on the tax side. So that bromance doesn't last long, and they decide to form, as part of the Budget Control Act, this is BCA, one of the acronyms, as part of the Budget Control Act, they decide to form the Super Committee. So full of prominent politicians and other folks. You can see them up there. I don't even remember everyone who was on it. Senators, I see John Kerry and others. So that failed. Right, they were supposed to come up with $2 trillion in savings over a decade, and they couldn't agree. So all of a sudden, a bunch of bad things that you've heard about start happening, the sequester. So the bottom line here is where we ended up because the super committee failed. Had the super committee found this $2 trillion grand bargain, we would have ended up on the line below, which still isn't great. So again, you have the second President Obama agreed that deficits were a problem, we were in this kind of trajectory. We couldn't get out. So the thought was, this bottom line is going to be so painful that we're going to have to come up with a grand bargain to find this $2 trillion, so we're in the less painful line above. So stepwise, every couple of years, the Republicans and Democrats would get together and they would pass 2-year fixes. Like, oh, we can't handle how bad that's going to be, so let's add a little money. When Obama was in office, there was an absolute requirement of what they called non-defense discretionary, that's another one of the acronyms, NDD, that non-defense discretionary and defense discretionary have parity. So for every dollar you increase defense, you have to add $1 to non-defense. So they did this a bunch of times, and even most recently, this is the most recent one, so they keep adding money. So we're back to that chart. Where we actually end up is in the blue. And the most recent deal, which could be solid blue if this was a fully updated slide from the folks at AAAS, would be where we are in the red. So this orange dash line is still what was in President Trump's budget. So this is, and remember, he's got Mick Mulvaney and others, big budget cutters. So this is really where the Republicans would like to be for non-defense discretionary. So you've got this going on, Congress adding money, larger deficits every couple of years. Then here's a real interesting thing I thought was bogus when I first heard it. There's such a thing as on and off budget. I thought everything's on budget. What does that mean? There's either a budget or there's not a budget. Well, it turns out that the politicians have created off-budget things. So all those caps that we talked about in the Budget Control Act, all these things don't apply to anything I'm about to talk about. GWAT, there's another good acronym, Global War on Terror, after 9/11. And now it's sort of translated into OCO, another acronym, Overseas Counterterrorism Operations. So the way that Washington's been funding a lot of post-9/11 DOD activities is through things that don't count against any of those caps. So they can agree we need more readiness here or there, and they just add money on top. It doesn't get tracked on any budget cap agreement. There's also, of course, disasters. This is the Disaster Relief Fund, and you can see years when there were big disasters and money gets added in supplementals. Here's sort of adding both OCO, the light blue, to defense, and then in various years where they add emergency spending. My wife is on the House Appropriations Committee, and right now they're working on the next emergency supplemental. And the emergency supplemental that is part of her bit is to build a plant for flu vaccine that's not reliant upon chicken eggs. So this has been a big thing. People want to do it. It costs about $2 billion. But she can never find money for it in the CDC budget. So you just wait for one of these emergency vehicles to drive by, and you kind of jump on and try and justify your thing and why it should be funded outside the caps. So this leads to folks who don't like spending, folks at the Heritage Foundation, which largely populate now the Trump administration, saying that Congress has to stop abusing this, even though both sides do it. Here's the most recent one, just this summer. That red dot where they have the most recent budget deal, $1.7 billion. Here's the most recent supplemental. This is interesting, right? And this is another Paul Krugman bit, right? Interest rates are so low that it's cheap for the government to borrow. So this is actually lower than CBO's Congressional Budget Office's projection. Then they thought interest rates couldn't possibly be that low. So the government's just saving money, not having to pay as much interest as people had projected it would. So this leads to, if you ever want to, I don't know whether it'd be depressed or just go to sleep, you can read some of these Congressional Budget Office projections that show, on this case, their most recent projection, what's happened, the average deficit prior to 2018, and now the average annual deficit as a percentage of gross domestic product in these projection years. So you can see the end of Clinton that people like to talk about, the few surplus years, and then the response to the Great Recession that's mostly lost tax revenue. So all those annual bits add up to total debt held by the public. And in the projections, we're now beyond what was World War II and the debt incurred. So this is why, again, the people that think we should stop spending money will always point to these charts, but Dick Cheney notwithstanding. So we're going to get to the point of why you should care now. Because non-defense discretionary houses research and development funding, which houses science and astrophysics funding, this 12%. And empirically, it's always 12 to 11% of non-defense discretionary. So whatever happens to non-defense discretionary directly impacts how much money is available for projects and grants. So this is going to continue. You see non-defense discretionary is continuing to get squeezed. Mandatory keeps growing. And so until deficits matter, we're doing really well. So you have to sort of hope that the Dick Cheney rule holds, which must be really conflicting for many of us in the room. That's it. Well, economists make lots of arguments on how big is too big. You know, when are people going to stop lending the United States government money?
That's the thing. It's an international.
Yeah.
Let's start with you.
Was this true even during, say, the moon years where NASA was going to the moon? I thought we had
The moon bit is here. Where's that? Oops. That was not true. The percentage, the empirical percentage, that's the Apollo program.
That's the, so what we need is another Apollo program in order to boost the level.
Right, so another Sputnik, I would say. That's why I thought,
China landing on the moon?
well, I thought the best way to get more money would have been, you know, the first Chinese rover that failed, they need to launch it and then like drive over the U.S. flag. And then money would just pour forth from the government.
NASA is actually contemplating going back to the moon, but it's not really space. It could be quantum computing.
Yeah.
It could be some other challenge that the nation as a whole is engaged in. For example.
Well, apart from having other nations do things that may cause us to either respond by doing something or by declaring victory, so it's, what can we actually do that's positive that might help to either protect us as cuts come down the line, or may even bring us to more positive attention so that...
This is pretty good. This is pretty good.
Yes, but as you pointed out, it may not always be, you know, if deficits do matter. So just, you know, what can our community do to inoculate ourselves against times that may not be quite as good?
Become independently wealthy. So, you know, it's hard in these, if we go back to what was, people talk about in infrastructure or that Recovery Act, the vast majority of the money went to things that you would think of as, you know, shovel ready, you know, literally building roads and things like that. The only reason that science is in there is Nancy Pelosi. Okay, so one person in a particular position can really influence how much money goes into science, making the argument that this is part of the infrastructure of the U.S. I was at the Office of Management and Budget in the White House then, and trying to get National Science Foundation to push out, this is the, or, you know, they need a committee meeting to talk about committee meetings at NSF. They take a year to do everything. To tell them you need to spend this money now, it's got to be done, you got to have spent it and improve the economy. That's a hard argument to make, but people understood it. But it was one individual that really pushed all that. So you have to talk to your members of Congress. I think there's somebody who lives around here who's running for president. You know, there you go. So.
But one thing to keep in mind is in the current landscape of funding science, significant funding comes also from the private sector and commercial interests, especially in space science right now. So it's not just the government. We have funding sources that are private that, you know, at least contribute more than half actually of science funding in research.
Mostly in biomedical, yeah.
But still, that's another resource.
Yep.
Okay, if there are no more questions, let's thank
All right, thank you. Oops.
Where is the mic? Thanks.
Got it?
Sorry, because... Okay. Now it works. Hello, everyone. Again, I just delivered the ITC colloquium, and I think I'm talking too much for today, which is something, unfortunately, happens to me quite often, that I talk too much. So Now I'm going to talk to you about supernova-driven MRIs, and I hope you'll not get bored by this. This work I've been done in collaboration with Elisa Bortolas, who's now a postdoctoral fellow in Zurich. So extreme mass ratio inspirals, MRIs, occur when a stellar-sized compact object, a neutron star or a small black hole, spirals onto a supermassive black hole emitting gravitational waves. And studying MRIs is particularly exciting because the LISA mission will be able to observe MRIs up to ratio 2 or even 3, and this will give us invaluable information about the mass and even the spins of supermassive black holes. So it's quite important to understand them now, to study the formation mechanism of these events. And the most popular formation scenario for MRIs is via two-body relaxation. So two-body encounters can perturb the orbit of a compact object and transform it into an MRI. During my short talk, I will show you that there is also an alternative mechanism, which I will call supernova-driven MRI. So let's look at our galactic center. Isn't it beautiful? It is the closest galactic nucleus. It hosts a supermassive black hole, which is few million solar masses, which is about the right size to produce an MRI. Good. Sounds promising. It is surrounded by a dense star cluster. This is also good for MRIs. And a fraction of stars in these star clusters are massive and young. The S cluster, the clockwise disk stars, are about few million years old, which means that they will undergo supernova soon. And when a star explodes as a supernova, it leaves a compact remnant, and the compact remnant can get a natal kick. So the basic idea here is that the kick perturbs the orbit of the compact object and can transform it into an MRI by removing angular momentum. If we want to quantify this effect, we cannot neglect the rest of the nuclear star clusters, which is going to perturb the compact object with two-body encounters. So we model the background cluster in two ways to bracket the uncertainties, which is considering a heavy background of other dark remnants or a light background of light and older stars. And, the best way, I think, to visualize MRIs and what is an MRI is with the semi-major axis versus eccentricity, one minus eccentricity plane. And in this plane, you know that if the orbit is very eccentric, then we have a direct plunge into the black hole. So a direct plunge means basically no detectable gravitational waves unless the direct plunge happens maybe in the Milky Way, but this is very exotic. Second time scale we should care about is the time scale for coalescence by gravitational wave emission. The violet line here shows the region where the times for coalescence equals the Hubble time. So on the right hand of this line, there are no MRIs. On the left-hand side, there may be, but you still need to consider one thing, which is two-body encounters. If a compact object ends up here after the natal kick, it may still get perturbed by two-body encounters, which can either facilitate the MRI or send the orbit back to the region where coalescence is not possible, where MRI is not possible. We want to be very conservative, so we assume that two-body encounters always remove the MRI. So we define this green line as triangle as the region where the two-body relaxation time scale is longer than the gravitational wave time scale, the time scale for coalescence. And if the compact object ends up in this green triangle, we are pretty sure that it's going to become an MRI. So this is the framework. Now we can simply run some analytic formalism with some Monte Carlo to understand how many stars will produce MRIs this way. And here you see, again, the semi-major axis versus 1 minus eccentricity plane. We set up initial conditions choosing a mass function for the progenitor stars, distance from the supermassive black hole, so semi-major axis, initial eccentricities. We do this for several reasonable distributions in the galactic center, like the clockwise disk. Here you see the example of the clockwise disk. So these contours there are the progenitor stars assumed to be in the clockwise disk. We do this for S-cluster, for other distributions. And in the right-hand panel here, you see what happens to the compound object after the natal kick. We assume some distribution for the natal kicks too. And you see that a non-negligible fraction of the compact objects ends up in the green triangle. So these are going to be MRIs, supernova-driven MRIs. We can repeat this trick for several other distributions of the progenitor stars, and we quantify what is the fraction of MRIs over the total number of supernovae that can happen in the Milky Way. Sorry, not in the Milky Way, just in the galactic center. This plot here shows the fraction of MRIs with respect to all supernovae as a function of the semi-major axis, initial semi-major axis of the progenitor star for several different distributions of the progenitor stars that we consider. I highlighted when the progenitor star is in the S cluster and when it is in the clockwise disk. Well, with these very simple fractions, we can use back-of-the-envelope calculation to estimate the order of magnitude of supernova-driven MRIs that we expect from our own Milky Way. The number is about 10 to the minus 8 per year. Well, unfortunately, we won't be able to observe this from our own Milky Way during the LISA mission. But if we assume that Milky Way-like galaxies do supernova-driven MRIs this way, and only Milky Way-like galaxies can do it, which is quite conservative, then we end up with a supernova MRI density, rate density of about 0.04 per gigaparsec cube per year. And convolving this number with the LISA mission features, we expect LISA to detect a few tens of supernova-driven MRI per year. That's nice. It means that this alternative scenario to produce MRIs is important for the observation with LISA. And I like to stress that there is a very strong feature that helps distinguishing between this scenario and the two-body relaxation scenario. From supernova-driven MRIs, we expect most MRIs to happen with neutron stars or light black holes, which are the ones that possibly get the fastest kick, natal kick. While we don't expect many supernova-driven MRIs from the 30 solar mass black holes that we observe with LIGO and Virgo. In contrast, with two-body relaxation-driven MRIs, the most massive black holes are the most effective one in producing MRIs. So, well, I'm done. If you're interested, just ask me, or here is the paper by Elisa Bortolos and myself. Thank you very much.
On the gas that will bring the progenitor stars or the neutron stars closer to the center, and by that enhance the rate significantly. So you don't need to rely on the kick from the supernova to bring the neutron stars close in. Of course, it could do to also bring the black holes in, but what I'm saying is it's possible that even during a short phase of gas-dominated environment, you could still bring more neutron stars than on average.
Yeah, this is a very good point. Actually, as I said, we started by considering the galactic center, and our supermassive black hole now is quite alone and lonely with not much gas. But definitely, what I think is important here is what kind of eccentricities you expect, but I think, yeah, that would be fine. So it's definitely something, yeah.
Questions?
Yeah. Most likely not.
Let's thank Michela again.
Hi, so lovely to be here, and this talk is going to be slightly different from all the three we heard, though probably closer to Michela's talk. I'm going to talk about something which we can do, which is gaining a lot of interest in the recent years and hopefully in the coming decade, based on this innovative technique which has been pioneered here by Avi and others in observations known as intensity mapping. And there are signs to indicate that this technique can allow us to do very exciting fundamental physics, possibly exploring beyond the standard model of lambda CDM we are all familiar with. So essentially, just a very brief primer what intensity mapping is. Most people will be familiar with this. But essentially what it is a traditional galaxy survey just resolves individual objects, individual systems. So this is like an example of a CO survey with VLA, for example. And instead of doing that, what you do in intensity mapping is to just have a smeared out image of the same surface, of the same kind of area, but without resolving individual systems, thus making it a very fast and effective probe of both astrophysics and cosmology. And you can do this with different lines. So for example, you can do this with 21 centimeter, which gives you clues about the intergalactic medium, about reionization, and other exciting things. And you can do it at other scales, like smaller scales, interstellar medium. You can do intensity mapping instead of doing traditional surveys of the CO molecule or the C+ molecule in different sources. So essentially, when you do an intensity mapping experiment, you're doing something like the CMB with baryons. So you're really looking at integrated intensity of radiation, and you're measuring something which is very akin to the CMB temperature power spectrum. So it is a temperature power spectrum, it is fluctuations, but it essentially contains some part of the underlying astrophysics of the tracer, which is basically causing the radiation, as well as the underlying cosmology, which we're familiar with and which we'd like to constrain in an experiment. So we'd like to think about how the CDM power spectrum changes with different redshifts and whether that indicates something going wrong with LCDM or anything else. Or we might like to look at the evolution of H. But we need to understand that when we do intensity mapping, we have to grapple with this interplay between astrophysics and cosmology, which leads to what one would call an astrophysical systematic effect in these surveys, right? So in order to efficiently handle this astrophysical systematics, over the last 4 or 5 years, collaborators and I have developed this method of looking at cosmological neutral hydrogen. So looking at all the data we have today in neutral hydrogen in the post-reionization universe and building up a 5-parameter model of how the H1 populates dark matter halos, and constraining this parameterization from all the data we have today in neutral hydrogen. Just the way people do it for dark matter and for basically galaxy evolution with occupation, you can do it for baryonic tracers, and it worked much better than we ever thought it would. It led us to surprisingly precise constraints on a fiducial model which was best matched to the combination of all the data. So doing this for a baryonic tracer has a lot of advantages, and the first important advantage from the point of view of cosmology is that it allows us to overcome and understand this astrophysical systematic in intensity mapping. So the way you can do this is that just as you do for the CMB, you do an angular power spectrum, which is just that linear power spectrum in redshift bins, which is observable to us. And you know that it depends on cosmology in a particular way. And through the halo model, you know how it depends on the astrophysics. And you can put very accurate and realistic priors on these astrophysical parameters coming from precisely all the data we have today. When you do that, you can use very standard techniques, statistical techniques like Fisher matrices and things like that, to make precise forecasts of cosmology and astrophysics in the presence of each other via this halo model from the angular power spectrum. And this allows you to do several interesting things. So the first thing is that when you do forecasting of cosmological observables, you can actually understand how much the astrophysics is influencing cosmological forecasts from future intensity mapping surveys. Unlike the CMB, intensity mapping is something which will get you a huge amount of range of redshifts. It gets you a lot of modes, so it explores a lot of volume. So when you do that, you can actually potentially achieve very good constraints, and you can also quantify how much the astrophysics may interfere with those constraints and how you can remove it cleanly. And you can also ask how this works for different experiments which are going to be out very soon or are already running, such as the CHIME in Canada, SKA, and several others. So this also tells you something interesting, that what we found is the degradation in the astrophysics, which naturally happens because of that first formula, because astrophysics comes into cosmology with intensity mapping, is very much compensated by the sheer tomographic coverage of current and future surveys, so which is a very positive thing which we found. One of the chief challenges in intensity mapping is foregrounds, and foregrounds really cause problems which are 10 to the 5 times more than the signal. But foregrounds can be taken care of with the same picture with a halo model framework by cross-correlating galaxy surveys and intensity mapping surveys, both of which we have formalisms for. So shown here is an example of a CHIME-like survey and a DESI-like survey cross-correlated to do very nice forecasts on both astrophysics and cosmology. And what you can also do, up to now I told you about precision of constraints, you can also look at the accuracy of these kind of constraints, because you might be very precise, but you might be off the right value. And this you can alleviate by, again, looking at the halo model framework for baryonic tracers and asking how nested likelihoods, there's again a formalism developed for that. So statistics allows you, once you have the priors, to understand how much astrophysical shifts, a misunderstanding of the astrophysics, will bias your cosmological tracer and bias your cosmological constraints and standard parameters. The most exciting thing it gets for you is what I described in the first slide. Is it lambda CDM or something else? It turns out that you can actually use this in a very straightforward way to uncover deviations from lambda CDM. You just put that model into the cosmology and model the astrophysics precisely using the halo model. A very interesting extension is the primordial non-Gaussianity parameter and existence of a non-zero FNL. And what we find in the latest work is that it's very gratifying that even when we put in astrophysical uncertainties, FNL constraints are very negligibly affected by these kind of uncertainties. But to quantify this and to go further, we really need to combine our astrophysics and cosmology correctly, which is what we can achieve through the halo model. So exciting times ahead with current and future experiments. Thank you so much.
There are two areas where we can gain knowledge. One is the initial conditions of the universe, the composition, what we call cosmology. The second one is astrophysics, galaxies and so forth.
Exactly.
And there is this underlying theme in many discussions that one is superior to the other. Like, let's minimize the contamination of the lack of information we have on galaxies in order to figure out things about the universe. But it could be turned on its head and say, you could say, let's use the microwave background to figure out cosmology, which we pretty much did to a very good precision. And now let's learn about galaxies.
Absolutely, absolutely. So one person's foreground is another person's signal. And this is really the place where this is one of the chief reasons we developed this Halo model framework, because really the astrophysicists are really interested for reionization, galaxy formation, and comparing to simulations. So that's one of the things which is an extension of this in that direction. So for today's talk, I basically focused on cosmology, but there's a huge amount of exciting astrophysics you can constrain, including reionization. Yeah. Oh, yeah.
Yeah, thank you. That was a lovely talk. In terms of where you go from NAM to CDM, the other direction I've heard a little bit about is going to what framed in others called warm dark matter,
Yes.
because of the satellite galaxy distribution.
Yes.
I wondered if you looked at
Yes.
what that did to your statistics.
So we're looking at this with collaborators, Göttingen and other places who are experts in these kind of models. So where the warm dark matter comes in is really different from where the FNL comes in. So it's really affecting the power spectrum, so the K dependence of the power spectrum. So we really need to look at that. It does affect it in some way, so it's still preliminary, but I think the direction is very straightforward. You just figure out how much the H1 astrophysics is influencing the small-scale shape of the power spectrum, and that's a bit more complicated than FNL because it seems it is much more tied to astrophysics, so we can't really probably say something clean with that.
So this astrophysics model,
Yes,
which you kind of calibrated already
exactly.
before doing the cosmology, it has some handful of parameters.
Exactly.
Right? Can you say a little
Sure.
bit more? What is that model?
What is it? So essentially we wanted to parameterize the H1 to halo mass relation given a dark matter halo model. How does H1 mass follow halo mass in an average sense? And in a deeper sense, how does the profile change with scale and redshift and mass? So it's exactly like a dark matter halo model, but it needs to have more free parameters in it because basically you need to constrain. For example, this is telling you about an overall normalization of H1 to halo mass. This is telling you how H1 mass is sloped beta with respect to halo mass. So it's kind of telling you that this need not be unity. So it's need not be proportional. It can be different at high mass n, for example. And this tells you basically, this is like a virial velocity cutoff. It tells you how small galaxies should be so that they preferentially don't host much neutral hydrogen. So all these parameters are physical. And similarly, you have concentration and concentration mass parameters and their evolution, which is dictated by the small scale physics. So these 5 parameters are found again by series of experiments to be the most statistically, favored parameters given all the data we have today. So for example, with SKA, we might have a lot more data, but given what we have today, we find that the 5-parameter framework is the most constrainable, and we achieve, more surprising constraints on this than we expect. These can all evolve. And some of these parameters are evolutionary parameters.
Yeah, but for example, in the early universe, there was much more H1 in galaxies.
Absolutely.
So that is not captured.
This is only up to redshift 6, 5.56.
I was wondering about the AGM.
Right.
If there's a bright quasar, it probably kills most of the H1.
Absolutely.
That is not included.
That is
here.
not. So because it's a statistical framework, it's basically taking the average and taking the column density distributions and so on. Yes.
Could you now figure out the variance around that average?
You can do something like a scatter analysis, but that will require, which is what actually a student is doing right now, to compare with simulations. like the AGN simulation, putting in different kind of feedback, and he is actually quantifying the scatter. That's very exciting. That's definitely something, yeah.
It's not just the feedback. There is also the issue that in clusters of galaxies, the gas is too hot. It doesn't cool to make H1. So
Also,
there
yes.
is an issue of cooling of the gas in the halo to make the H1 in the first place before it's destroyed by feedback.
So that is actually somewhat captured by this one, because that tells you about the UV radiation and also the cooling, the temperature to UV, which kind of goes into this. But this one parameter captures, as Avi was pointing out, a huge number of physical processes. So to exactly unravel that would need a help of simulations. That's true. And more data, definitely, because, yeah. And more. Yeah. Thank you. Was it in time? I didn't hear the...
I don't know, but people didn't seem to care. So.
Yeah, but I mean, was it? It didn't go about time.